let's move on and go right into the first slide. So when we talk about machine learning, there are essentially three major categories of disciplines in machine learning that we'll touch on briefly. The first one is the category of classification algorithms. And these are used to really take data and break it down into, say, buckets or classes for a given input. So this is really good for taking data with lots of variables and then trying to say that this, if you want to think about it as a stream of data or a group of attributes that make up a document or row of data, whatever container of information you want to refer to it as, how does this get classified? And one of the easiest ones to start with is a decision tree. Now, most machine learning algorithms, what you do is you have what's called a training set of data. So what you do is you start off with a set of data that you have already, it's already classified the way you want. And what you do is you hand that to the model, and the model learns from that training set. And all of these models have different ways of changing configuration values or changing strengths or values, what values you want to use as part of your decision tree or the classification algorithm as a whole, and which ones absolutely don't apply when trying to classify the data you'd like. But as you run through the training model, the machine learning algorithm learns from that training data. Then you run test data through the same thing. Now, the test data, you remove the desired output or classification, but you know what it is. And what you're doing is you're testing, did the machine learning algorithm learn from my training model or training data? Did it learn what I wanted it to do? And then from there, you can turn it free on your data and go from there. Now, a decision tree, like I said, is the kind of the easiest one to think of because we kind of do it every day, whether we know it or not. A decision tree is simply a workflow. You get presented with data and you go, is this number higher or lower? Oh, it's lower. Okay, well, is the color blue or red? Well, it's red. Well, you just made two decisions and walked through a decision tree. And that's what machine learning does, but it does it at a deep learning level where once it's trained, I can put into it lots and lots of data and have it crunch through it very fast. And here's a good use case. So a medical use case that we've actually used here at BurstIQ is for chronic kidney disease. And what we did is we had this wealth of information, and chronic kidney disease has categories or classes, and it's 1 through 5. 1 being early stages, 5 being a chronic case. And each case has a set of criteria that depend on blood work, age, and a multitude of factors. Well, you can train a model to go through data for patients in bulk, if you will, and go through all this information and reclassify them as information changes about each patient, how new lab results come in, or if they've aged, or if it's been so long since their last dialysis, et cetera, et cetera. So all of these factors can allow a computer to go through and check on patients and move them through stages. And of course, then you can get into all sorts of things on how to alert the doctor or the hospital or whoever if something has changed in that patient. Now we're not spending lots and lots of healthcare provider time going through each patient record trying to understand where they're at. So there's a very real use case with classification algorithms when it comes to something like that. Okay, category 2. When we're moving into a little more different types of approaches. And one of the things that I'll stop and talk about real quickly is, machine learning isn't a black box. You can't dump a bunch of data into it and say, I want this, turn a crank and get it. There is a lot of data science and data understanding and data knowledge that has to come into play as you use these different algorithms, because I have to understand, do I have a multi-variable input and I'm looking for a single output? Is my data more organized in a collinear fashion, or is it more random? Do I have one input that affects one output? And then what kind of result am I looking for? And all of these come into play on which category you pick. And then you also, within each category, which technique is the best for you. So this is where I can, now, if you want to think of it this way, Linear regression is probably the easiest one to understand on this page, but it'll give you a basis for how regression algorithms work. If you think of a simple X and Y graph, and you put a dot on the graph, you've essentially put a dot at two locations, an X and a Y value. Well, let's say you have 1,000 of those. There is a way to train the model such that each input along the X has a predicted value along the Y, and there is a line that goes through this group of data points, so that the next time you introduce a new X, it can calculate what its predicted Y should be. And again, depending on the data and depending on your outcome, this might be a very good regression algorithm to work, or it may not be. And this is partly where you get into lots of having to understand the math and the formula behind these. But once you pick one and you train the model, the repeatability of the results is very impressive, which is why there's so much work that goes into the front part of data science and machine learning. But once it's trained, you can really get a lot of use and very rapid use out of these models. So we'll go into category 3 and move along here. Clustering. Now, clustering is I'll tell you, is the most fun and most interesting of the 3 algorithms to me, because this is one that has an unsupervised learning aspect to it. And this is where if you have data that has multivariables, doesn't have a linear function to it, and you know you're looking for how different data and points belong together. Now, if you start thinking about where I'm going with this and start thinking about graph databases and how data is organized, there is a natural clustering of information when it comes to graph databases. So how can we train clustering algorithms to take the inherent data and context from a graph model, for instance, and apply different clustering algorithms to it? So the best analogy I can give for you this is if you have a bunch of random dots on a page, and then you start looking for patterns where different dots are spaced different distances from each other, there then becomes a grouping that appears. You begin to identify what's called feature sets or feature points within the group of data. And then these different types of algorithms here, there's 4 listed here. The k-means is probably the most used to start with. And that will then give you the idea of this group of data belongs together, this group of data belongs together. So when new data is introduced, I can identify that belongs with this group. This belongs to, say, category 1 of a chronic kidney disease grouping, or stage 3 or stage 3B, et cetera, et cetera. So all of these different types of categories really apply and work very well depending on your use case. And so at BurstIQ, part of our data pipeline and part of what we're doing with the platform around life graphs is beginning to understand relationships that may or may not quite be apparent to the user, but they're in the data. And these types of algorithms, clustering and regression, will give us insights into how data is related to each other in ways we didn't see before. So we'll move on from here. So I already talked about this a little bit, but let me dive into a little bit more. As I alluded to, graphs are a natural representations of things we see every day. I already talked about social graphs, where they exist in LinkedIn and Facebook, how our brain networks are wired to be used, hierarchical imaging clustering. So a project I've worked on in the past at a previous company for doing Department of Defense work was doing image recognition and was actually doing clustering around feature sets on an image in order to identify moving parts from one image to a next. And it's a very, very interesting field of study because it starts training computers on how to recognize images. And that's where you start seeing things on the web where I can put up a picture and it'll predict, oh, this is a person, this is a car, this is a bridge. And so that's all because of clustering and feature set analysis in images. And it's a really fascinating field to study. Let's talk about contextual data again, because that's really what adds another set of value to data. So as we all know, they've talked about data being the new oil, the new petroleum. It's got inherent value. Context just adds to that value set and opens up a new doorway for us. Now, finally, I like this quote by Jim Weber. Neo Technology is actually the company that makes Neo4j, that graph database I referred to before. And machine learning doesn't depend on graph databases in order to work. You can use machine learning with all sorts of data input. But there's a basic efficiency of how storage and traversal of information within a graph is beneficial to machine learning. So at the end of the day, graphs can be inputs into machine learning, but it can also be a natural output of machine learning. And so my personal belief is you're going to see graph databases become out of its little niche pocket of where it exists in data science today, and it's going to grow rapidly. And I think there's going to be new types of machine learning evolved around this aspect of how graph databases can be used to unlock different types of insights. So at this point, I'm going to pull Frank back in because we get to talk about some use cases. Frank.
Yeah, as long as I can click without giving everybody, making everybody's stomach.
I'm not sure if you should drive.
Maybe have to back off a little bit of this. That's for sure.
You got to stop drinking so much coffee.
Too many buttons to push. Okay, AI and health systems sample use cases. I think you can see these things really start clustering together around what would be more deep learning type applications versus edge intelligence. So over on the right, research. A lot of AI being employed, particularly in the pharma space, around gene editing and research, genomics, proteomics, cellular biomarkers, drug discovery, and how drugs interact with us as individuals, drug effectiveness, and of course broader population health. So you saw a lot of real data science go into the generation of a lot of the COVID vaccines, and really being able to get those into market a bit faster versus traditional methods that were employed in the past. Over on the left side, person care. This is where you start seeing more edge intelligence begin to emerge in the form of wellness and early detection. I love a lot of the science around early detection. That's not only looking at data about you as a person, but also able to look at how you're moving and your motions and even emotions. To determine kind of early indicators and the onset of certain diseases. Obviously, patient engagement being used quite extensively now in the form of, again, chatbots and outreach and adherence reminders is all kind of lumped in these categories. We're going to see really, again, an emergence of personalized medicine and personalized health, and we'll talk about that in a second. And definitely companion therapeutics. If you have a certain condition or comorbidity, you're going to have a digital kind of narrow intelligence kind of help you navigate through that condition. On the bottom, clinical, a lot of push around clinical diagnostics and clinical decision support. That gets to be a pretty complex data science area because we as individuals are different. We might have some of the same basic makeups in terms of components within our physiology, but everything about us then starts to vary. So as you traverse down, really trying to figure out what's wrong with somebody, it can get a pretty complex decision tree from that perspective. But this is where you're going to see a lot of cooperative intelligence emerge in terms of kind of companion diagnosis systems to suggest that a physician may look at things or to see kind of correlations between certain medications and treatment factors and how what would maybe unrelated medications are actually being having a positive impact. Last, robotics. See robotics in the operating rooms today, and it helps overall with kind of recovery, less impact on our bodies when we're able to do things from a micro perspective. And even what you're going to see, I think, in this dimension is ability, for us to ingest things that are smart and intelligence that can help a physician navigate our condition. And then finally, operations. A lot of work around fraud detection, particularly on the payer space. Operational optimization. We've done a lot of work in AI around revenue cycle management in terms of figuring out patterns within rev cycle, both from a provider and a payer side of life. Training is a big one. Virtualization and all this virtual reality is really going to help accelerate training and efficiencies across the board. Scenario planning, we're kind of seeing this come true with some of the previous scenario plannings with pandemics. We're pretty close to mirroring what transpired with COVID. So scenario planning with disaster recovery and such is a big issue here. And last but not least, where we like it or not, marketing in terms of how we get this kind of mass marketing coupled with this micro targeting to us as individuals. And last, we're kind of excited about this one emerged because we've been doing a lot of research with some partners around the whole aspect of ambient and ambient technologies. And ambient's another discipline within artificial intelligence that takes a physical thing and represents it in cyberspace or virtually. A lot of work initially around IoT devices and in creating a virtual representation of an IoT device, but even more energy really kind of pushing down this path of creating an ambient twin or a AI representation of yourself that's able to go out and do things on your behalf, and also interact with you in a very constructive way for your own health and well-being. So kind of love this dimension. It's both exciting and can be a bit scary, but we see a lot of possibilities here if we're able to address some of the broader ethical considerations around artificial intelligence.